on scattering theory, but it will not be the final time we see Sebastian, as tomorrow he will be giving a colloquium here discussing some modern viewpoints on scattering theory applied to three-particle systems, for which you see he's preparing you for tomorrow with some example on the board. So Sebastian, you can start.
1, 2, 3, can you hear me? Okay, good morning. I'm impressed that so many of you survived yesterday's dinner and show up today. Those of you watching this at home later on YouTube, shame on you. But remember to like, subscribe, and click the bell. The sponsor of today's episode is Unitarity. I started writing on the board because we have a lot of material to cover during this last lecture. So let's see if we can do it. So we'll talk about unitarity. I wrote it down here just to remind you how it looks like. I told you during previous lectures that it implies appearance of some branch cut discontinuities, so-called right-hand cuts. As you remember, we can consider amplitude as a function of many complex variables, but for reasons that are sort of experimentally important and for simplicity, we will focus today just on partial wave projections of the amplitudes. And this is mostly because in experiments, you really want to extract states of well-defined angular momentum. And the simplicity comes from the fact that we will not have to consider angular dependence of these objects. So I will show you how to derive unitarity for the matrix element of the scattering amplitude of the scattering operator after partial wave projection. It takes an extremely simple form that will lead us to the so-called K-matrix parametrization, or something that I think in the nuclear, like hardcore nuclear theory world, is sometimes called R-matrix parametrization. If we will have time, I'll mention throughout this lecture the left-hand cuts that come from cross channels, as you remember, which are also implied by unitarity in the cross channels. And then we will talk about dispersion relations, so we'll make a huge circle going back to this dispersion relations appearing in Titz-Marsh theorem for these causal transforms, and we'll talk about N/D equations. This is extremely ambitious plan for today, so we'll see if we can make it. Okay, so first step that we are going to make is remind ourselves that there is something like cluster decomposition. So this principle that tells us if we have two events that are separated, they should not affect each other. And you can formally write it or express it by decomposing your S operator, scattering operator, into two pieces. One that is just identity, so an operator that describes nothing happening. Whatever came in, comes out with no scattering. And then there is transition operator T, which describes some actual process taking place. We sometimes call this a disconnected part of the scattering operator or scattering amplitude, and this is the connected part. In the 2-to-2 scattering, this will be the full decomposition. I wrote here this tiny almost connected part, because if we start considering multi-particle reactions, this part will also have to be expanded. It will have some disconnected pieces in it as well. Now, if we plug this decomposition into the unitarity equation, one either left or right-hand side, we will arrive at this form of the unitarity for the transition operator. So we just want to get rid of the uninteresting part. Is there a question? No question? And that's what the form that it takes. And already from this equation, we can see that there will be discontinuities in the amplitudes. Might seem surprising at first because, I mean, how, why? To understand it, it's good to just for a moment introduce some diagrammatic description of these objects. This will not be Feynman diagrams. we will introduce some diagrams to essentially describe two-body matrix elements of these operators. So essentially what it means, this blob will mean the S operator, and these two legs will mean that we, on the right-hand side, compute its value on some two-body scattering state. I haven't defined it yet. I will define it in a moment. And on the left-hand side, two legs mean that we have some two-body cat on the left-hand side. Identity is a simple diagram. It's just no scattering, no blob required to describe any kind of reaction. It's just initial line going to the final line, nothing happening. And to distinguish T from S, I'm using this full blob for T. So if you sandwich these operators between these cats describing two-body states, physical states, so on-shell states, and introduce here decomposition of identity into these states, you will arrive at this diagram. So essentially, T minus T dagger will become an imaginary part of the matrix element. This is up to certain factors that are absorbed in definitions of objects, and this will be equal T times T dagger, as you see here. And this line means that these particles that we, over whose momenta we integrate, the integration is given by the fact that we introduced here decomposition of identity. These momenta are on-shell, so we have to remember that these lines describe on-shell states. Mm-hmm. Yeah, the difference is just that this is the full S operator, and this is just the connected part, the T transition. So I'm just using a full blob to distinguish these diagrams. This diagram will not appear here, right? Because this is expressed just in terms of T, but it will appear in a moment, as you can see on the board. What's the difference between S and T? This and that. T is just S minus 1. So T is an operator that describes scattering, getting rid of the uninteresting part. No scattering at all. Yes, very well. We sandwich, and we'll do it more carefully in a moment, but we sandwich these operators from left and right with two-body states, two-body momentum states, and this T is a blob like this. T dagger should be a blob conjugated, but let's ignore these details for a moment. Don't pay too much attention to this picture. It's not really properly explaining what I will explain later. I'm just trying to give you some intuition how it looks like. And then we sandwich the right-hand side as well and plug your decomposition of identity into this two-body states. So we get two diagrams, they are connected, and that's what we get. Well, but you could say, okay, and I said we immediately see there's this discontinuity in the amplitude here, because this object describes some abrupt change in the energy variable of the amplitude, because if there is not enough energy in the system to produce an intermediate two-body state, there will be no such thing, there will be no connection here. So there must be something happening on the right-hand side of this diagrammatic equation when we reach energy that allows us to create a two-body intermediate state. And this contributes to the imaginary part of the amplitude, which we associate with discontinuity of the amplitude in the complex plane. To give you an even more intuition about that, imagine that we have enough energy to create a free-body intermediate state. Well, then in the decomposition of identity in our Hilbert space that can be decomposed into blocks of certain energy, we have to include states that have free-body states, and that would correspond to diagrams like this. So there is certain energy that if we reach this energy, we need to include additional contribution to this equation, unitarity equation for the scattering amplitude. So if there is additional particle, additional intermediate state that just appears at a certain energy point, it must be a discontinuous change in the imaginary part of the scattering amplitude. And these discontinuities associated with the creation of this two-body, three-body, four-body, etc. intermediate states, these are two-body, three-body, four-body production thresholds, so energies at which we can excite two or three and four-body states. Okay, so we already have some intuition that some kind of discontinuity must appear in the amplitude. Exercise for you, consider 3-to-3 scattering. You can write the S operator as an identity, just like before. And then, as I told you, there will be a more complicated structure sort of imposed by cluster decomposition, because in addition to the fully connected piece of the amplitude, where all three particles are involved in the interaction, there is a possibility that only two of them are involved and the third one doesn't care, just flies by far away. Well, there are three options because three of those particles can not care at all. And if you take this decomposition and plug it into this equation, essentially, you should arrive pictorially at this type of formula. So this is an exercise for you. And you will see that this 3-to-3 scattering amplitude, this is unitarity relation considered above the three-body production threshold. We'll have discontinuities from the three intermediate states. It will also have discontinuities in kinematical variables describing two-body subchannels. That's what this diagram describes, in the initial and in the final state. And it will also have this special type of diagram where particles interact only through two-body transition operators, but they can exchange a physical particle between them. So this is not an exchange in the sense of Feynman diagram when we exchange virtual particles. It's a really physical particle that sort of leaves the pair of these two particles and can propagate for infinitely long until it somehow accidentally hits this particle, interacts with it, and emerges as two in a pair. No, it's on shell. Everything's on shell, yes. Yes, because this is not Feynman diagram. This describes a process, as I said, where three particles come in. One of them is far away, but these two are close, but they interact so strongly that one gets kicked in the right direction on shell. So they interact, these are on-shell particles. One gets kicked in the right direction, the direction of the third one, just travels for a long, long, long time until it gets so close to the third one that they start feeling each other, interacting. This one travels far away, and then these two interact and scatter. So this is not a virtual exchange. This diagram contributes additional right-hand singularity, additional right-hand discontinuity in the three-body unitarity equation, and it's responsible for very interesting physics. This was a question? Mm-hmm. Yes, if you think in terms of this typical language in three-body states, spectator pair or dimer spectator, yes, this you would call this spectator, you would call this an interacting pair. Here you would say there's a change in the meaning of what pair is, because the pair in the initial state is different than a pair in the final state. And it's purely a kinematical effect. Okay, an exercise for you. It's just multiplying pictures together. If we want to really properly define what these diagrams mean, what are these matrix elements, we need to define what the scattering states are. So we say we will now stick to two-body scattering. Our scattering state is a product of single particle scattering states. Single particle states are just momentum. We'll consider them now just to be momentum eigenstates that are normalized in this relativistic fashion. It can also be made into an exercise to show that this is a Lorentz invariant normalization. And given this normalization, we can decompose our identity operator in this sort of complicated form, which I'll explain. This is a sum over number of particles in the Fock sector that we consider. This Fock sector is characterized by some energy. So the Fock sector opens only if you reach certain energy. In other words, you can decompose Hilbert states not only by the number of particles, but into energy blocks. And, well, you have to integrate over momenta of intermediate states. I put here I, meaning the state of I particles, for example, 2, 3, 4. And you have to integrate over all these intermediate momenta. Here's a simple example. Just for two-particle scattering, you have two intermediate momenta. You integrate over them. You have two cats, and theta function that describes that this Fock sector opens when you have enough energy that is equal to the 4m squared if we think in terms of Mandelstam's S variable. Just for completeness, this omega p is my notation for the on-shell energy of a particle. And it's also important to remember that when you consider scattering of identical particles, you need to symmetrize your scattering state because, well, they can have flipped momentum. For most of the lecture, I will ignore symmetrization and then just restore symmetrization factors when they should appear. And I won't explain that. It will be an exercise for you to figure out where these factors of 1/2 should go. It's a question.
I could imagine pi plus, pi minus, and pi 0
Mm-hmm.
interacting, going to a pi 0 intermediate state, which then splits into 3 violence again. What keeps this imaginary part of the T matrix to go into only one intermediate state instead of 3? You know what I mean?
Not sure.
So, if I understand you correctly, that last diagram on equation 2 is the case where you have a single particle intermediate state. But those other diagrams have, I mean, so there's really 3 particle intermediate states, just 2 of them are speculated on that last diagram. But you can have 3 particles in your intermediate state that are interacting with those first 2 diagrams, right? Okay, I'm not understanding.
So in this picture, let's say the pi plus and the pi minus would interact to go to a pi 0. We would exchange a neutral fire. And then this firstly spectator, pi 0 would absorb that neutral fire and go into pi plus, pi minus.
Yes. Okay, so that clarifies. Thank you, Andrew. It gave me time to write this. Okay, so another thing we need to write down properly, what is the matrix element of this transition operator on these two-body states. And we will write it in this particular form with the explicit for momentum conservation delta function. So for momentum is P1 plus P2 or P3 plus P4, where these are considered 4 vectors now. So this is both energy and momentum conservation. And we know that the amplitude is Lorentz invariant. It can be described in terms of 2 Mandelstam variables. T, as you remember, is related to the scattering angle. This was squared, 1 minus cosine theta. So you can also express the amplitude as a function of Mandelstam variable and an angle between orientations of relative momentum in the center of mass frame. So this is a valid variable. This is essentially this cosine theta thing here. And it will be a little bit easier at some point to think of amplitude in this form. Okay, so if we want to properly derive what this diagram means, what this looks like in terms of matrix elements, we just have to sandwich our T operator between two-body incoming and outgoing states, and I'll just write down the answer almost immediately. There should be, maybe I shouldn't be using these stars. Oops. It's equal to, and now I will introduce a shorthand notation, integral 2. Integral 2 means essentially that. Maybe I'll pull Heaviside theta outside of the integral because it's an important fact that the threshold opens at I mean that the two-body states are open at threshold. So now there will be one orientation of two-body relative momentum from the final states, and then there will be orientation from the intermediate state. I will call it something. Okay, I used Q and Q here, which is inconvenient. So let's say that this integral 2 is an integral over variable K1 and K2. And of course, you can also show that this integration, how you call it? I don't remember, not normalization. Measure, integration measure is Lorentz invariant as well. I think that's a typical exercise during quantum field theory course. But if you want, I can show it to you later. Okay, so there will be some K star hat, and then there will be M, S, Q, K star. Here, there will be complex conjugation here, and there will be complex conjugation here. So these stars on momentum orientations mean center of mass frame. These stars here mean complex conjugation. Okay? And you can show that assuming T parity, so time reversal invariance, that daggering T leads just to M conjugated because of the symmetry between incoming and outgoing state under the time reversal. So that's a comment I should make. And now the question is, how do we perform this integral? I just write the answer and a single intermediate state that might cause some problems because otherwise it's relatively simple. You just want to evaluate it in the center of mass frame and use the fact, oh my goodness, I haven't finished writing this. There is a for momentum conservation delta function, which is important, and this Heaviside theta. So the fact that you have 4 Dirac deltas under the integral over 6 variables will mean that you can immediately integrate out 4 of these variables, or almost immediately. I'll show the one non-trivial step. And you'll be left with an integral over 2 variables here. We will choose these variables to be angles giving you the orientation of this relative momentum in the center of mass frame. So the non-trivial step is doing this final Dirac delta integration. So essentially, you take the integral over the remaining momentum that stays here after you use momentum conservation and get rid of one of the momenta. And I'm using K variable, different than in my notes. and you write it in spherical coordinates, what you will have here will be something like that. This omega squared k star comes from going to center of mass frame and multiplying these two omegas, which become the same, as you remember from the exercises. And then you are left with the angular part. So this is two-dimensional integral over the orientation. And I divide it by 4 pi for convenience. This is essentially based on how the spherical harmonics are normalized. Then this Dirac delta, maybe I should finally write it down. It's Dirac delta of energy times Dirac delta of momentum, total momentum. This will be the one that remains under this integral after we get rid of one of the momenta. And we can rewrite it as a Dirac delta over magnitude of the relative momentum minus magnitude of the final relative momentum. How did we get this from there? It is just using transformation properties of Dirac delta. So this is this one non-trivial step that I wanted to write for you, which I see I didn't write in my notes. So let's do it from memory. So essentially, what we have after getting rid of one of the momenta is that this remaining energy conservation Dirac delta is that. Two energies of single particles must be equal to the total energy. And now this can be written in terms of magnitude and now we know that a Dirac delta of some function x is equal sum of I Dirac delta of x minus xi inverse of absolute value of the derivative of f, where xi's are zeros of this function f of x, so places where this Dirac delta is non-zero. So in our case, if we do this derivative over k star and use this formula, we'll get, as far as I remember, probably the factor of 2 will be wrong somewhere. Actually, we can write q star here. Delta of q star minus k star, which is what appears here. And maybe I've made a mistake already. Yes, because this is to minus 1. And this should be included here, which I forgot to do. So let me write it down here. Okay, I hope this is correct. So what we did, let me just repeat the steps. We took this integrals to center of mass frame. We got rid of one momentum using this momentum conservation. Then we rewrote our integral in the radial or spherical coordinates. And then we just used some property of Dirac deltas to write it as a simple delta that can be immediately integrated out using this integral. And there's this bunch of factors that appear. So essentially, this integral becomes what I wrote here. This together with Dirac delta. Without theta, so just for completeness, let me include theta somewhere to make this formula even more unreadable. Okay, final answer is imaginary part of M is equal to whatever we get from here. I say imaginary part because this is M minus M conjugate. There's I, we can divide by I, divide by 1/2. This gives us imaginary part and gives us 1/2 here. Will be Q star divided by M 8 pi E star, so energy of the system, but I will write it as square root of total invariant mass. And then this leftover integral over orientation of intermediate momentum in the center of mass frame. Okay. This one. This one. Oh my goodness, I'm forgetting stars, primes, everything. This is madness. Okay, so we simplified the formula. There is this two-dimensional integral left, as I promised. How do we simplify this integral even further? Before I tell you this, there's a symmetry factor from symmetrization of states, which would be 1/2 if particles are identical, which is really what we want to consider here. And then this factor, energy-dependent factor, I say energy-dependent because you remember we can consider, my goodness, was it S minus 4 M squared? We can write Q in terms of total invariant mass. This factor with 1/2, so this will be called two-body phase space. Okay, what do we do about the integral? I told you we don't care about angular dependence during this lecture because we want to simplify things. And there is still angular dependence left here, so what we need to do is to partial wave project. Oh goodness, I will not get to N over D. So, partial wave projection, how is it defined? We essentially have a function of angle. We can decompose it into this orthonormal set of functions that remove angular dependence from the amplitude. And this partial wave decomposition can be written like this. Yes, prime star, Q star prime. And spherical harmonic here. So essentially, we decompose the dependence on angles or orientation of this relative momenta in the final and initial state into spherical harmonics. So one spherical harmonic will take care of the angular orientation in the final state, one in the initial state. We need to sum over all angular momenta. So this sum goes from 0 to infinity. These sums go from minus L or L prime to plus L, L prime, as usual. And this decomposition comes from essentially the decomposition of, or the relationship between the state, momentum state of a given radial momentum. This is something you remember from quantum mechanics, I'm sure, into a state of well-defined angular momentum. Okay. So essentially, you can write your amplitude in terms of this angular variable sandwich between angular, Katz, or there should be some here, or sandwich between this angular momentum states, and this is what defines your partial wave projected amplitude. Using the rotational properties of LM states, which again you probably remember from quantum mechanics, Wigner rotations, etc., and conservation of angular momentum, which is another important principle, you can write that this amplitude just really depends on a single angular momentum, and then it's just a bunch of delta functions. So this comes from angular momentum conservation. And this also comes from angular momentum conservation, but you see it by studying rotational properties of these states. So this becomes a very simple decomposition. I mean, if you use the so-called addition theorem for spherical harmonics, you can write it as a single Legendre function. Where we have to sum over L here and over M. It's the sum over L and M or just L? I don't remember. I think, yeah, over L and M. And there is star somewhere, I believe here. Yes, you're right. It's sum over M because L is here. Okay, so you can write it as a simplified way. And there's probably some 2L over 4 pi, of course. So let's put this 4 pi here. That's why I pull out this 4 pi here. And the correct theorem gives you 2L plus 1 divided by 4 pi. Okay, so essentially, by using these Kronecker deltas under the sums and using the theorem for addition of spherical harmonics, you can write this in an even simpler form, like that. And you recognize that when we were talking about non-relativistic quantum mechanics and scattering there, where we included angular dependence in the Schrödinger equation, the function, the scattering amplitude f that we defined also came with these Legendre polynomials in front. Okay, so why do we perform this partial wave projection? I remind you, we wanted to get rid of this angular integral inside the unitarity relation to arrive at the partial wave projected unitarity relation. But now we remove the angular dependence from the scattering object, and we can now integrate it if we know enough properties of spherical harmonics. So I will let you do this step yourself. This will be your exercise, which is plug this decomposition that I will call equation 3 into what I will call equation 4. So take this, read it in terms of spherical harmonics, plug it here, plug it here. Remember that there are different orientations here, so there will be spherical harmonics with different orientations. Plug it here, and integrate over angular dependence, which will just give you a bunch of delta functions from the orthogonality of spherical harmonics. So after you do this, this whole expression will simplify drastically. So go from 4 to 3 in the way that I just described to you. And the resulting expression will be very simple. So if you didn't follow any of that, start paying attention now. Resulting expression will be this. And I need to highlight it with at least 2 colors. As I said, this is the crown jewel of S-matrix theory, at least in two-body case. Partial wave projected unitarity. Why? And it's wrong. Because, of course, I forgot something that I should never forget. There is this theta that tells you this equation holds only above the two-body threshold. So if you made a box in your notes, just make it larger like I did right now. So this equation that holds only for these energies above the threshold. Why is this equation important? First, it tells you there is a non-zero imaginary part above the threshold. Imaginary part and real part that appears in the modulus squared of the amplitude in this equation are related to each other. Should ring a bell from the dispersion relations that I showed you for the causal transform in this classical mechanics example. There we could relate imaginary part of causal transform to its real part, and this is what this equation does. And if we treat a partial wave projected amplitude as a complex function of complex S, we'll see that this equation leads to a square root branch cut discontinuity starting at the threshold as promised, because this object, which I will write down again, so now it has 16 pi over square root of square root of S, goes something like square root of S, and square root of S was this function that is multi-valued and defined on two complex planes. So you see that imaginary part has this discontinuity, or the function in general has this discontinuity. Now, there's an important relation that I mentioned already several times, so-called Schwarz reflection principle. That tells you that if you have an analytic function that is purely real on an interval on the real axis, its value in the upper and lower half plane are related to each other in the following way. Amplitude of the complex conjugate of total invariant mass is the complex conjugate of the amplitude. What does it mean? It means that value of the function here at some s and value of the function here at some s conjugated will be related by a conjugation. So the difference between function at point A and the difference between function at point B, let me write it down, will be just m at point A minus m at point A conjugated. And this is imaginary part up to factors of 2, etc. Okay, let me put this factors of 2. It will be an imaginary part of the amplitude. But this is discontinuity of the amplitude across the cut. We know there is a discontinuity. If we go here, there will be some jump in the value of the function when we reach point B. So imaginary part of the amplitude is equal to its discontinuity across the cut. That's why I've been always referring to this discontinuity, this equation giving us discontinuities of the amplitude. So I hope it starts making sense now. Okay. So there is another neat way of rewriting this equation. I mean, there are many ways of rewriting this equation, which lead to different parameterizations of the scattering amplitude. Because as I told you, since imaginary and real part of the amplitude are related to each other, we just need one real function to describe the amplitude, and you have a freedom in choosing what this function will be. Mm-hmm. No, it's not. It is an assumption, I would say. Andrew told me this morning, we argued that it can be proven in 2-to-2 scattering, but not in higher multi-particle scattering. I think it should be provable also for higher particle scattering processes. Okay, the Bros-Epstein-Glasser theorem that I mentioned yesterday, it's not a theorem for the partial wave projected amplitude, so maybe there's no immediate connection there, but it says that if you fix t at appropriately negative value, there will be a real interval between your S and U cuts. Okay, so right now we can consider this an assumption, but I am almost sure that it can be shown that the amplitude satisfies Schwarzschild reflection principle. Okay, so let me repeat that. Schwarzschild reflection principle tells you if amplitude is real on the tiniest of tiniest intervals on the real axis, it must satisfy this property. Conjugation of argument leads to the conjugation of function. And that means that the difference between function across this continuity, so at these two different points, can be translated into difference between amplitude and its complex conjugate, which tells you that this continuity across the cut is equal to its imaginary part. And I'm giving this example for two reasons, or I'm explaining this for two reasons. One that I have already mentioned, one that I will hopefully mention in 5 minutes. The first reason is I wrote you this diagrammatic expression, or the unitarity relation, which is a relation for imaginary part, but I kept using words, there is a discontinuity. Or in some sense, I was suggesting there is some equivalence between imaginary part and discontinuity of the amplitude. And this is the basis for this statement. Okay? The second reason is this is important when you start deriving dispersion relations for the amplitudes. This connection between discontinuity across a cut and imaginary part allows you to replace contour integrals that go across discontinuities as just real integrals over imaginary part of the amplitude. This is the second reason, but I'll mention it in a moment. And it's also, remember this principle for tomorrow's talk, because it will be funny how it works in the free body case. So just another comment. Okay, I told you you can describe amplitude in terms of one real function because there is this constraint of what kind of functions we can use in scattering studies. And it can be either scattering phase shift. So essentially, you introduce polar decomposition of your complex function. That's a complex number. It has a radius and it has a phase. And this thing we call phase shift. And using unitarity relation, you can show that the amplitude itself can be written in this way, which probably you have seen. So you can choose phase shift to describe scattering. You can show using unitarity relation. It's extremely simple. That this is bounded by 1. You can introduce another clever geometric idea called R-Grant plot, which is rewriting this equation as a parametrization of a circle. So you can rewrite unitarity in this form. Well, it's imaginary m squared plus real ml squared. But if you just completed a square, you will see that it's a circle of a certain radius. So you can write it as, I think that's how you do it. This was equal to 1,4. So we have a circle centered on 1/2, where this is imaginary m axis times rho. This is rho times real m. And the points on the circle are given by 2 times phase shift. You can make your scattering experiments and see if the amplitude that you get lies on the circle. So if it satisfies unitarity, because this form of unitarity just follows from that. If it starts deviating, which often happens, that probably means you hit some higher multi-particle or 2-particle threshold, and this 2-body elastic unitarity no longer works. You have to add something called inelasticity, but I won't have time to discuss that. And then there is this parametrization of the scattering amplitude that allows you to make a connection to some microscopic descriptions, which is called the K-matrix parametrization, which is missing from my notes. So I'll try to describe it from my memory. So notice that this unitarity relation can be also written as a formula for the inverse of the scattering amplitude. Just essentially divide left and right-hand side by m modulus squared, and notice that m modulus squared is just m times m star, and just cancel m. And you'll see that this must hold. So the imaginary part of the inverse of the scattering amplitude must be a known function. Well, so what can it be? It can be something that is a real part, and we call this real part the inverse of the K-matrix. So we introduce another object that must be an analytic function above the threshold. It cannot have any singularities, because all the singularities above the threshold are constrained by unitarity. Unitarity only allows for this square root branch point, if we consider 2-body elastic unitarity. So this K matrix will be general, a real real function with no imaginary part. But of course, below the threshold, it can be whatever because of this theta. And then there's imaginary part that's given by unitarity relation. And this is what we call the K-matrix parametrization. Okay, if you read any papers on scattering, either in the experimental or lattice QCD context, you will see this object a lot. It's extremely commonly used. Let's discuss some maybe properties of this K-matrix. So K-matrix can be related to the solutions of the real Lippmann-Schwinger equation or Bethe-Salpeter equation. What do I mean by real Lippmann-Schwinger and Bethe-Salpeter equations? Original Lippmann-Schwinger equation looks something like this. I think there is. For the transition operator, if instead of taking this resolvent, so these are all operators, this is potential, this is free Hamiltonian. If instead of taking this resolvent of the free Hamiltonian with I epsilon and replace it with the principal value, so remove I epsilon, I'll define principal value for you. Principal value of an operator is defined, essentially as a real part. Up to some factors, as usual. Then the equation that is satisfied, then the object that satisfies such an equation is the K-matrix. This is the off-shell K-matrix, and just like this is an off-shell transition operator, but by putting it on-shell, you will get the K-matrix that appears in the on-shell amplitude we wrote down here. And there's similar procedure in the Bethe-Salpeter equation that I won't write down. Just need to, again, define what the principal value prescription means for a product of two propagators appearing in the loop for the Bethe-Salpeter equation, or what taking real part of the Bethe-Salpeter equation means. Another comments about K-matrix. Sorry? Yes, but there are two different epsilons, so deltas should cancel, right? Because they have different. This cannot be correct because if I take and evaluate imaginary part of this object, no, it cannot be imaginary part because this one will be delta of plus I delta, and the other will be minus I delta, so they add each other, so there must be a plus here. Thank you, you're right. Okay, let me see if I can find some other comments on K-matrix. Okay, here they are. In principle, since Lippmann-Schwinger and Bethe-Salpeter equations are so complicated, we don't know how to solve those equations in some complicated quantum field theories, like QCD. So, although we can get some hints, maybe, what we do is model K-matrix. We know that it has to be some real object, and it cannot have these singularities above the threshold. So, in practice, we model KL or KL to inverse. And sort of typical models are effective range expansion, or some general model for either KL or KL inverse, I'll put it in parentheses, that consists of some sum of poles at some positions plus a polynomial in energy. So sort of a general ansatz you can write. I should put J here and J here and J here. K-matrix is related to the scattering phase shift. So we can relate these two different parametrizations if we want. This will be square root of S minus 1, Q star cotangent delta L. Yes, thank you. And I mentioned we should include also left-hand singularities in the amplitude from unitarity of the amplitude in the crossed channels. So since we have this cut in the S channel, and the amplitude describes the crossed reaction, where the S, Mandelstam S, is T or U in the original reaction variables. As I showed at the end of the previous lecture, this will lead, the unitarity in this cross-channel S, Mandelstam S variable, will lead to a left-hand cut in this amplitude, partially projected amplitude considered as a function of S. So these objects come from virtual processes, thinking now in terms of Feynman diagrams like this or that. So this is the diagram that corresponds to unitarity in the cross-channel, because we have two particles that can go on shell in the cross-channel reaction, and so on. And there are other contributions. Now, unitarity relation constrains K-matrix only above the threshold in the S variable. So all these left-hand cuts can go into K-matrix. So all dynamical, the dynamical input that you might want to model using your Bethe-Salpeter or Lippmann-Schwinger equation that essentially takes a form of some Feynman diagrams describing your forces, coupling, particles being exchanged. All of this dynamical input goes into KL. KL can have left-hand cuts, which represent some dynamical input. Okay, I ran out of time, but Andrew is very merciful, so he will let me tell a few more things. Generalizations. What if you want to consider particles with different masses, coupled channels, so possibility that incoming particles are different from outgoing particles? Let's still stick to 2-2 scattering. Essentially, this KL object becomes a matrix In single channel case, although we call it K matrix, it's not really a matrix, it's just a single number. In the coupled channel case, this K matrix will really become a matrix in the space of considered channels. Other generalization includes things like possibility of partial wave mixing. So if you consider not coupled channels but particles with spin, this partial wave projection becomes more complicated. And partial wave mixing is allowed. So no longer there is a constraint that tells you L prime has to be equal to L, because orbital angular momentum can switch if you have particles with spin. The total angular momentum, which is J, that's the sum of orbital and spin, cannot change. And then this KL object also becomes a matrix in the space of possible angular momenta. I will not write it down, or maybe I can write it down here. Space of, let's call it LM, angular momenta. This is when we consider particles with spins. This is when we consider more channels. What people usually do in terms of modeling when these cases are considered is they use something called Blatt-Biedenharn parametrization. To describe the system. This is a very neat way of parameterizing partial wave mixing scattering. In the coupled channel, what's typically used is Flatte parametrization that was mentioned by someone during one of the talks. But of course, these are just parameterizations. You can come up with your favorite way of parameterizing K matrix. And now dispersion relations. No, I think I have to stop. So thank you. Please ask me a question about dispersion relations.
Let's thank Sebastian. Okay, any questions?
It's a very good question. Let me please give you a more elaborate answer to that question. So, as I just drew, we understand, and after 4 lectures, we understand now the analytic structure of the amplitude pretty well. It has right-hand cuts, it can has left-hand cuts. It can have a bunch of poles here, but let's ignore bound state poles for a moment, for simplicity. We said we can relate imaginary part to real part. We said we can write many different representations of this unitarity equation. And people came up with an idea that allows them not only to satisfy unitarity, or to write a parameterization of the amplitude that not only satisfies unitarity, but also ensures proper analytic structure of the amplitude. And to do this, they consider the following theorem that I think we all know by heart now, the Cauchy theorem for the partial wave projected amplitude. So, since amplitude is an analytic function almost everywhere except for these discontinuities, let's pick a integration contour in the Cauchy theorem that looks like this. and has some right orientation that gives us right sign, which I never remember what it is. I think it's that. Okay. But now, if our amplitude decays fast enough on the large circle, which will be our assumption. If it doesn't, one can use something called subtractions. So you can always write an ansatz for the amplitude such that this large circle will go away. The equations will look a little bit differently. You can just say that this integral is equal to an integral from the position of the left-hand branch point, or from -infinity to the position of the left-hand branch point, over imaginary part of the amplitude plus an integral over imaginary part starting from the threshold to plus infinity of the imaginary part of the amplitude. Why do we write imaginary part of the amplitude here? Because of the Schwarz reflection principle. We know that the amplitude here is related to the amplitude here, and we can replace the difference between them, where the minus sign comes from the direction of the integration along our contour, with an imaginary part. And there should be no 2i factors, which is correct, because these 2i factors over there actually were important. So there's just 1 over pi here. Okay, so people realized that if you write your amplitude like this, unitarity tells you what this imaginary part is here. You can write it as the square of the amplitude itself. Right? This is an approximation because the elastic unitarity doesn't hold up to infinite energies. So it is an approximate representation of the amplitude. And you can use this equation as an integral equation to solve, where this is an input. Note that this is amplitude modulus squared, so something like cross-section, multiplied by rho, so something like intensity. So this is something you measure experimentally. You can parameterize your experimental data, plug it here, and imaginary part of the amplitude on the left-hand side is related to your dynamical model of one particle exchanges or two particle exchanges, Feynman diagrams, effective field theories. And by ensuring consistency between this piece and the amplitude that this equation is for, you can extract information about these dynamical processes that go into your modeling. Something like coupling strengths between hadrons, etc. A problem with this equation is that not the Fredholm equation. There is a Fredholm theory of integral equations, which tells you that if integral equations are of certain type, you will arrive at unique solutions. There's no proof for this equation that you can get a unique solution. And that's what N over D is for. You can rewrite this dispersive representation of the amplitude in the form of two coupled integral equations that are linear and satisfy Fredholm theorems. This is based on the so-called Wiener-Hopf technique, where you write, in this context, you will write the amplitude as some numerator over some denominator function, and you will say that this numerator function contains just left-hand singularities, denominator function contains just right-hand singularities. And from these simple assumptions or this simple decomposition, you can write those integral equations and solve them without worrying about uniqueness of the solution. Well, there's still a lot of other things you need to worry about. Sorry? Yes. Yes, you can always perform such a decomposition under certain assumptions.
Half decomposition, you need some region where the analytic structure is distinct from each other. And
Yes.
that's what you have here, because you have left-hand cuts and right-hand cuts. So you can do this decomposition.
Okay, thank you for that question. I can, if it doesn't satisfy you, I have another 2 pages of notes.
We're starting to run a little into coffee time, but
Yes.
Which I think for today some people need. But are there any more questions for Sebastian? Yeah, we shouldn't, we should still take questions.
Hi, thank you for your lecture. If for some reason there were bound states inside the counter, there will be residue?
Yes.
Oh, okay.
So if you consider poles, you just need to include residues.
The summation over.
Yes, summation over residues.
Oh, okay, thank you.
Any more questions? Okay, we can always bug Sebastian more. He'll be here, and tomorrow he'll tell us about 3-body physics. Let me just say thank you very much for volunteering your time.
Thank you for having me.
Yes.
To all you watching this on YouTube, again, remember to like and subscribe.
All right. Okay, so now we'll have the coffee break now.